the basic object, with defining the basic objects. So the most basic object is quantum dynamics. Okay, perhaps it's not so basic. Okay. Anyhow, that's what I'll talk about, and I will be interested in the space L2 of ZD, the d-dimensional lattice, and I will restrict myself to d equal 1, 2, or 3. So the quantum dynamic. So I have a self-adjoint operator on this space on L2, and I consider the following dynamics. We start with a function psi in this space, and after time t, it goes to psi t, which is e to the I th psi. So if you have never seen this object before, and if you have seen Markov dynamics, let me compare the two. So Markov dynamics is the following. We have a particle which lives on the lattice, and it has some probability distribution pi, which tells us what is the probability to be at every side of the lattice. And then we have a matrix P, where on the xy place we write the probability to jump from y to x. And on every step it jumps according to this probability matrix. So after n steps, our distribution will be p to the power n times the original distribution pi. Now there is a slightly more sophisticated object, which is a continuous time Markov dynamics, which I won't define, but it's more or less the same. Pi goes to e to the t times something called the generator of the Markov dynamics times pi. This is pi t. So if we compare this to this, we see that the difference is mainly this imaginary unit in the exponent, but it's quite a significant difference. So intuitively, psi is the wave function, so the probability distribution is the squared absolute value of psi. This is not formal. And since the operator is self-adjoint, the total L2 norm is preserved, so it somehow makes sense.
You want that to be pi, right? Or
yeah, sure. Okay, so what I will be interested in is the speed of propagation, which is the following. We start with psi equal to the delta at 0, which is a function which is 1 at the origin and 0 at all the other sides of the lattice. And then we apply our quantum dynamics, goes to psi t. And then we can ask how far does our quantum particle go, which means that we consider the average of the average distance from 0, and the average is according to this probability distribution, psi t of x square. Well, there are different ways to define it, but I'll just take the simplest way.
Do you assume some conservation invariance?
Pardon?
Do you assume some conservation invariance?
Well, I will tell you in a minute which operator I consider. I will consider one very specific operator. It's not translation. It's distributional translation invariant. But so this is somehow the average distance from 0 after time t, and there are different possibilities. For example, there is one possibility which we rarely meet in Markov dynamics when this is uniformly bounded, and this is called localization. It's not very exciting in Markov dynamics. It happens only if somehow it's not connected, if we can't jump outside but here it happens, and it's not very formal, but it usually corresponds to pure point spectrum of the operator. And there is the opposite possibility when this grows like t. This is fast as possible, and this is called ballistic motion. And there are some intermediate possibilities, of course. For example, when it grows like square root of t, and this is called diffusion. And now I'm even more vague. Somehow, well, this is definitely not a general phenomenon, but for operators which I will consider, these somehow correspond to absolutely continuous spectrum. Okay. Now, okay, one more thing. Sometimes I will also need a slightly more precise notion. So this somehow doesn't depend on energy, and sometimes I need to do something more precise. So I fix an energy E, and instead of look at a small interval around E, say from E to E plus epsilon, and then instead of applying the quantum dynamics to the operator itself, I apply it to the spectral projection of H to the interval E plus epsilon. Which roughly speaking means that I erase all eigenfunctions which correspond to eigenvalues outside this interval, and say in the finite dimensional case, the spectral projection of a diagonalizable matrix, some lambda I vi tensor vi is the spectral projection is just the sum restricted to lambda in this interval. And then we can speak about energies for which we have ballistic motion, and energies for which we have some other phenomena. Okay, so now come the two examples which I will consider. So actually there will be only one example. The first one is random Schrödinger, also called the Anderson model. And after some, although it appears in the title of my talk, after some reflection, I decided not to say anything about it, except that some of what I will say about the second example applies to it as well. And the second one is random band, which I will define now. So it is a random operator which is constructed as follows. When the distance between x and y is less or equal than w, then these entries hxy are random, and iid is subject to the constraint that h of y x is h of x y bar, since we want the operator to be self-adjoint. And all the rest, and if x minus y is greater than w, then the corresponding element is 0. So if you imagine, if we assume d equal to 1, and you draw the matrix corresponding to this operator on the standard basis, it will look like this. You will have non-zero entries here and zeros outside, and that's why it's called a band matrix. Okay. So, and I will be mainly interested, so this talk will mainly be about the perturbative regime, which means I ask what happens when the parameter w becomes large. Okay. Now, so I need to tell you what is the distribution. I won't tell you exactly, but I need some scaling, and I will scale it so that the spectrum of our operator will be something like -1, 1. And then, it doesn't work like that. Okay. And then I'm interested in, so I need to rescale the distribution so that it stays the same. And so let me tell you, so there are very precise conjectures and even there's a very convincing derivation on the physical level of rigor, but hardly any mathematical results. So let me tell you what happens. In dimension 1, it is known from general theory, Furstenberg's theorem and its extensions, that any operator of this kind has localization. And the question is, so it's known that we have localization, and the question is what is the localization length, on what is the size of the box where most of the mass of the particle stays. So it's expected from the work of, so there are two predictions. The first one is that this quantity behaves like w square root of t up to some time t0, and then so it behaves diffusively up to some time and then stops. So it's w square root of t0 when t is larger than t0. And this t0 is expected to be w squared, and therefore the localization length, the size of the box where 90% of the mass of the particle stays, the localization length is supposed to be of order w squared 2, and this should hold for energies between -1 and 1, not on the edges. Okay, so what is known is much less. Is it possible to see anything here? So what is known is that the localization length is between w to the 8 and w to the 7/6. This is due to Schenker 08, I think, who extended the technique of transfer matrices to get some quantitative estimates. And the lower bound is a recent work of Laszlo Erdős and Dante Knowles of this year. So this is known for energies of this kind. On the edge of the spectrum, it's actually known. The localization length is actually known. On the L of ±1 is of order w to the 6/5. And this is me 2009. Okay, so now let's pass to dimension 2 and 3.
You said that the H is random, so
This means almost
Almost surely with yeah. Yeah. Okay, I will leave.
if entry is Gaussian.
It's not known. It's not known even if the entries are Gaussian. It is. There is one specific model for which there is special structure, and there are works by Spencer and Dissertori, and there more is known, but they're not exactly of the form which I defined. Here you can choose your favorite distribution. It won't become much easier, I think. So in dimension 2, the situation is much worse. It's expected that there is localization, and the localization length is of order e to the some constant times w. And what is known is that it is greater than w to some power 4/3, and this is again Erdős and Knowles, and less or equal to infinity. Well, this is of course not a theorem. I wrote it just to emphasize that we don't even know that it's finite. And in dimension 3, it's even worse. We expect diffusion when w is large enough, we expect, and nothing is. We only know the only thing that is known is again some power, some lower bound of this type, w squared. And this is again Erdős no less. Okay. So now in the last. In higher dimension, you expect things to get simpler, but I don't think there is something like infinite dimension, which is a Cayley tree, and there you can actually. Well, I think actually this model becomes trivial on the Cayley tree. There is a Anderson model doesn't become trivial, and you can prove something about this. But in I don't think even in dimension 1000 we know anything. Okay. I'm in the middle of the spectrum. So I was quite imprecise here. There are actually tails outside, and there we know quite a lot. But I'm interested in the middle of the spectrum. Here, on the edge, we know a bit more. So, for example, this I think it's possible to compute the localization length on the edges also for in higher dimension, but it's not so exciting. Okay, so let me just say a few words about technicalities. The thing that I'm interested in is perturbation approach, which basically means that I'm trying to expand everything in inverse powers of W. And there's a very extensive physical literature on this subject, and it gives very reasonable answers, which are a bit hard to justify. So let me show you some difficulties for an easier problem. So an easier problem would be to take the operator H, take its spectral projection to a small interval, look at the 0, 0 element, and consider its average. So, I ask whether this is bounded by something like epsilon. So if I wouldn't take the average here, if this would mean that we have absolutely continuous spectrum. So with the average, the problem is much simpler and actually tells us nothing about the original problem, but it's already complicated enough. So what is known, and it follows from Wagner's estimate, that there is a bound c times epsilon times square root of w. But this becomes worse as w goes to infinity, and we expect this is also true. Okay. So the problem is as follows. There is a way to expand on the physical level of rigor. When we can expand this, or even take a delta function at the energy E, and expand it into in a series sum of ck over w to the power k. But unfortunately, these coefficients grow like k to the power k, and therefore the series never converges. But it would be very nice to prove that this is an asymptotic series in some sense, or at least to justify, say, the first term. So this is currently unknown. So let's try something easier. Instead of a delta function, let's return to projection on an interval of positive length. So we take h e plus epsilon of h 0, 0. Okay, before that, there was one thing I wanted to say. So the coefficients ck are of very special form, and they are connected to very nice objects in enumerative topology. And they look like the sum of n greater or equal than k of n to the 5 over 2 k over 5 over, I write it in dimension 1, 5 over 2k factorial times e to the power I n times some phase, which depends on the energy. and times something else which which also depends on the energy and which I want write. So if instead of a delta function we take an interval of positive length, it allows us to introduce here a regularizing factor of the form phi of n epsilon, where phi is some decreasing function you can think about e to the minus n epsilon, or the indicator of 0 to n epsilon. So basically it allows us to cut off the part of the series where n is larger than 1 over epsilon, and so also to cut off all the part here where k is greater than 1 over epsilon. So it seems intuitive that one can so the game here is the challenge here is to make this rigorous for epsilon as small as possible, and it looks intuitive that one can do it for epsilon greater than 1 over w. So right now I don't know it, but this looks like a, I hope, a realistic project. Currently the best that is known is epsilon greater or equal than 1 over w to the 1/3, and this is again Erdős and Knowles. And the really interesting thing would be to get to epsilon of order 1 over w squared, or perhaps w squared plus epsilon, which seems right now unapproachable with this method. And I think I'm out of time or beyond time, so I'll stop here.